When we look at data, we want to look at its distribution. We want to look at the shape. That's why the histograms were important, as well as providing some graphical representations. The shape of the distribution can convey a significant amount of information. And when we look at the histogram, it begins to inform us of that shape. That's why the number of bins are also important, because sometimes a few extra bins will give us that shape and a few less bins might not give us the shape. So it's important to play around with it a little bit. The key characteristics are the breadth and the center of mass, as well as the skewness, defined by where the tail is. Does the graph appear to be shifted from the mean to the left or to the right? If it is left skewed, where the tail of the distribution is on the left, then it is called left skewed or negative skewed. If the tail of the distribution is on the right, then it's positive or right skewed. And if it's similar, the tails are similar on both sides, then it's symmetric or no skewed. Here are 3 different examples. So here we have positive skewed because the tail is to the right. The second one, the tail is to the left, so that's negative skewed. And the other one, we can clearly see that there's no skew at all. Now, we can compute a number for skewness, again using the .s and .p for skew.s, skew.p for sample and population, which will give us this number. The sign of the skewness indicates the direction of the skewness, negative or positive, but the magnitude of the number will kind of tell us whether or not there is a skew at all. And what we're looking for are numbers that are either less than -1, which would be highly negative left skewed. -1 to -5 is going to be, to -0.5 would be moderately negative or left skewed. If it's -0.5 to +0.5, it's approximately symmetric. Then 0.5 to 1 is moderately positive right skewed. Greater than 1 is highly positive and highly right skewed. Skewness, by the way, will also tell us the propensity of outliers within tails. The longer those tails are, the more likely we're going to have some outliers that may occur, because that's where the outliers occur. They're going to occur in the tails. Knowing how far an observation is from the mean can give us a relative location for any data point. Using the standard deviation with this distance provides a standardized relative measure of the distance. For any observation, the z-score is calculated by dividing the distance of the observation from its mean, that is xi minus x bar, over the standard deviation. The value is then interpreted as the number of standard deviations from the mean. And this process of converting an observation to its z-score is called the z-transformation. So let's take a look at what it might look like. We can show that the interpretation of the number of standard deviations is true. We've got the formula here to the right, xi minus x bar, divided by the standard deviation. The table below shows what the z-score is for a given set of values with a standard deviation of 5 and a mean of 20. If the mean is 20 and my observation is 20, well, the z-value is then going to be 0 because the numerator is 0. The observation is 15. We subtract 20, divide by 5. We end up with -1. Now remember, the standard deviation is 5, plus or minus 5 on either direction. Well, since we know that we're 5 over in terms of our observation, and the standard deviation is 5, that's going to represent -1 standard deviation. The same holds true on the right side. If we have 25 minus 20, the distance between that is 5, which is equivalent to 1 standard deviation. And computing the z-score, we see that it's +1, or 1 standard deviation away from the mean. If we had an observation of 10 and another one of 30, it would be -2 and +2, respectively, in terms of the z-scores. Using another example, data for students' test grades are here. The mean of the data is 86.25 and a standard deviation of 7.5. Thus, I can compute z-scores for each one of these items. For the 80, it's a -0.832. Now, it's negative, and it was below the mean, so the negative z-score does make sense. And it's about a little bit under 1 standard deviation because the standard deviation was 7.5, and it's only 6.25 off. So that means it's probably just under 1 negative standard deviation, which it is at -0.832. And you can do this for each one of these items. The one that's closest would be the 86 over there to the right, and in the third one, We have 0.033. It's slightly less than the mean, which was 86.25, but it's close enough to 0. And that's what we would indicate it as. It is very close to 0. In the case of 70, we're almost 2 standard deviations to the left. In the case of 95, we're 1.6 standard deviations to the right. We have a theorem called Chebeshev's theorem, which provides an estimate of the amount of data that lies between standard deviations. For any type of distribution, the following rule holds. At least 75% of the data will lie between 2 standard deviations from the mean. At least 89% of the data will lie between 3 standard deviations of the mean. And at least 94% of the data will lie between 4 standard deviations of the mean. Now, this is a little different than what we had shown before. Before we said in a normal distribution, the standard deviation would give us -1 and +1 was 68% of the data, -2, +2 was 95. This is a theorem for any distribution. Doesn't matter whether it's normal or not. And it says at least 75% of the data will lie between 2 standard deviations from the mean. Well, that still fits with the normal distribution because remember, in the normal distribution, we had shown that 95% of the data would lie between 2 standard deviations. So don't want you to get too confused with this, but this is the core theorem in which that other one was actually derived from. Now, the theorem provides a means by which actual boundary values can be obtained based on the z-score. So using this formula, 1 minus 1 over z squared, the minimum amount of data within z standard deviations from the mean can be obtained. So for example, if the z-score is 2, 75% of the data is found. If the z-score is 3, 89% of the data is found. If a z-score is 1.5, 56% of the data is found. And again, z must be greater than 1. So this is a way to identify what percentage of the data is found with a particular z-score in between a negative and positive of the z-score. As we said, Chebeshev's rule works for all data sets. However, when the distribution is known to follow a bell curve, we now know that 68% of the data lies within 1 standard deviation, and then that's that very dark red there. And 95% of the data falls between 2 standard deviations, which is a little bit lighter red, and 99% within 3 standard deviations, which is that tail red there, that little pink there to the bottom. The key here is outliers. Outliers are defined as data points that appear to be abnormal, and these will occur by the tails. Some of the data points can be shown to be an outlier by just examining them closely. Given a set of human temperatures, for example, right, we can see that 104.5 and 68.1 are probably outliers. Now, the 68.1 is clearly an outlier that can be caused by a bad reading. The second one, 104.5, is probably an outlier since it is extremely high, but the value is possible. It is possible, very dangerous, for a human being to have a temperature of 104.5. So it's important for the analyst to understand whether or not it is an outlier or not. Now, when we calculate outliers, the goal is to identify those outliers that are either too low or too high. When we had done our computations on interquartile range, which was Q3 minus Q1, this will be used as a concept to identify outliers beyond what we call an inner fence or an outer fence. These are what are known as Tukey fences, named after John Tukey, which provides a means to calculate both the inner bound and upper bound limits for outliers. So the inner bounds are more conservative, the outer fences are a little bit further, and so we would definitely say things beyond the outer fence are most likely really outliers. Beyond the inner could be outliers, but need a little bit more examination. And the way it works is this. We're going to take Q1 minus 1.5 times the IQR. So if the IQR was 22, we multiply it by 1.5 and we subtract that from the Q1. So that puts it all the way over to the left. And we'll take that same value and add it to the Q3 and puts it over to the right. We'll notice that the outer fences are twice as big because instead of multiplying by 1.5, we're going to multiply by 3. So here's an example where we're going to calculate the outliers for that same data set. The goal is to identify whether the outliers are too high or too low. Now recall we had these two, 68.1 and 104.5. So If I compute the Tukey inner fence, the lower limit is 96.1 and the outer limit is 103. And where did I get that from? Well, remember that Q3 minus Q1 is going to be 100.4 minus 98.7. So we can compute that using our IQR. We take that and we're going to multiply it by 1.5 and then subtract it from that Q1 number, the Q1 number being 98.7. So there we get our 96.1. On the reverse side, we're going to add that same number, 1.7 times the 1.5, and add it to the 100.4 to get a 103. So any numbers that are outside of that would be considered an outlier according to the inner fence. 68.1 and 104.5 are clearly that. But when we use the outer fence, we end up with two different numbers. We end up with 93.6 and 105.5. Because remember, we're multiplying that interquartile range by 3. And then in that case, only 68.1 is an outlier according to the outer fence.